So we saw last time that Einstein's special principle of relativity just consisted of two postulates, two very simple statements. The first being that the speed of light is invariant, so it's constant in all inertial reference frames. And the second is that the laws of physics, so not just mechanics, but all of physics, are the same in all inertial reference frames. And from these two very simple statements, we can derive a new kind of coordinate transformation, and that's what we're going to do. And we'll see that this coordinate transformation describes or has profound consequences for how we think about time and space. So in this section, we're going to derive this new coordinate transformation. And we'll start by thinking about two frames of reference. So let's think about one frame called S and a second called S bar. And we have that S bar moves away from S with some constant velocity u. Now we're going to think about an event. Okay, so something's going to happen. And let that something happen at time t in S and at position x, y, z. Okay, and we call this an event. And this event could be me shining my torch. Okay, so at time t and at position x, y, z, I turn on the torch. From the frame S bar, this event happens at time t bar, x bar, y bar, z bar. And we said that in Newtonian physics, there was the concept of absolute time, where there was some kind of master clock in the universe that ticked, that set every time. In that case, it would mean that t bar and t must be equal. But here, we want to relax that restriction and think about the more general case. So let's think about this event as being me turning on this torch. Okay, so I turn on this torch at time t, and the torch is located at coordinate x, y, z. Now let's think about a different event, a second event, and maybe it's an event, so I turn on the torch, that's the first event, and the second event is that the light from the torch reaches my hand. Okay, so this happens very quickly, light travels very fast. So let's think about a second event that happens at t plus dt, and a coordinate x plus dx, y plus dy, z plus dz. So that's from the perspective of someone sitting in frame S. So if you're sitting in frame S bar, then you see this event, the second event of the light hitting my hand at t bar plus dt bar, x bar plus dx bar, y bar plus dy bar, z bar plus dz bar. Okay. And the question is, how are these coordinate differentials related given what we know about Einstein's postulates? So given that the speed of light is constant as measured in both inertial reference frames. Okay, so the question is, how So how are these coordinate differentials related? How is t bar related to dt bar related to dt, etc. under or given the postulates of special relativity? Okay, so we're now going to think about how they are related, and we'll come up with a coordinate transformation. But the first thing we'll look at is the coordinate differentials. and this will tell us something about what is called the interval and the invariance of the interval, and that's what we're going to look at now. Okay, so we've got two frames, two inertial reference frames, S and S bar, which moves away from S with some constant velocity u. And the coordinates for each of these frames are as shown, so an unbarred set and a barred set. And the space that we're thinking of and the time we're thinking of are homogeneous. Okay, so we have a homogeneity of space and time, which is important. And what do I mean by that? I mean that if there is a clock that's moving freely through space, according to Newton's first law, so this is our clock, okay, and it moves freely through space, so there are no forces acting on it, it's a body in uniform motion. So each tick on the clock is an interval d tau, and each interval, so between each tick of the clock, the coordinate change in this set of coordinates must be constant. So that just means that one tick of the clock, the coordinates, the clock moves some amount of distance and some amount of time according to an observer in S. And at a later time, another tick of the clock, it must move the same distance and the time must increment by the same amount also. Okay, so there's no privileged point in space or time. Okay, so with that, we can say that the change in these coordinates, and let me call all of these four coordinates together x subscript mu, and mu runs from 0 to 3. So we're saying that the x mu, the change in any of these coordinates in an interval of time on our clock, so between two ticks of the clock, this must be constant. So in other words, if you're a clock and you're moving freely, then it doesn't matter if it's 5:30 or 9:30. If 1 second passes and you're in uniform motion, then the change in the coordinate at 9:30 must be the same as the change in the coordinate when 1 second passes at 5:30. Okay, so hopefully this is clear. And this also means that the second derivative of these coordinates must be 0. Now, the second postulate of special relativity tells us that the laws of physics are the same in all inertial reference frames. So if this is true in one reference frame, it must be true in the other. So this must tell us that dx bar mu by d tau is constant, and that the second derivative must be 0. Okay, and this one in particular tells us something useful about the transformation. So let's consider that. So let's look at these two things. Dx bar mu by d tau is equal to dx bar mu by d nu, dx nu, dx nu by d tau. Okay, so this tells us that d by d tau is dx nu by d tau, d by dx nu. Okay, so let's think about the second derivative. d2x bar mu by d tau squared, and this is d by d tau of dx bar mu by d tau. Okay, which is d by d tau of this thing, dx bar mu by dx nu dx nu by dt. Okay, and this is just a product rule. So this equals d2x nu by dt squared, dx bar mu by dx nu, plus dx nu by dt, d by dt of this thing, dx bar mu by dx nu. Okay, so let me write this here. It's d2x nu by d tau squared, dx bar mu by dx nu, and then we've got plus dx nu by d tau, and then d by d tau of this thing is dx, let's call it sigma, by d tau, d by dx sigma of dx bar mu by dx nu. Okay, which is just dx nu by d tau, dx sigma by d tau, d2x bar mu by dx sigma dx nu. Okay, and this is the second differential, d2x bar mu by d tau squared. Okay, but we said above that this thing must be 0. Okay, and we know that dx by d tau is a constant, so that the second derivative is 0. Okay, so this term must be 0 because it's got a second derivative. So this is 0. So the only way that this can be 0 is if this term is 0, but we know that dx by d tau is a constant, so these aren't 0. So for this to be 0, then this must be true, that this term is 0. Okay, so we find that d2x bar mu by dx sigma dx nu equals 0. So what does this mean? It means that our new coordinates, x bar, the partial derivative with respect to 2 of the old coordinates, the unbarred ones, is 0. Okay, so this means that our transformation is linear, i.e. that our x bars must be able to be written in terms of our unbarred coordinates with single pairs of coordinates. So the fact that our transformation is linear will help us to keep going in our derivation of the coordinate transformation. So let's think about the two frames S and S bar, with S bar moving with constant velocity u away from S. And let's think about two events. Okay, in the event 1, which happens at time t0, x0, y0, z0, and S. And let's think about that as shining the torch. Okay, so event 1 is the torch is turned on, and event 2, a second event, is when the light hits my hand. Okay, and event 2 happens at some later time, t0 plus dt0, and at a different coordinate, x0 plus dx0, etc. Okay, as measured in S. Okay, and in S bar, we have bars on these coordinates. Try and turn this torch off. Okay. So let's think about the distance that light can travel in the time delta t0. So we know that distance equals speed times time. Okay, and let's think about distance squared because it's simpler. dx0 squared equals, and the speed that light travels with is c. So we're squaring it, so it's c squared, and the time is dt0 squared. Okay, so we can take this to the left-hand side, and we have that dx squared minus c squared dt t0 squared is 0. That's in S. Okay, but in S bar, remember that light travels at the same speed as measured in any inertial reference frame. So whether you're in S or S bar, you will measure the light traveling with the same speed. So in S, the distance dx bar 0 squared minus c squared dt0 bar squared equals 0. Okay, and the speed of light c is the same in both cases. Okay, so this is true for our light ray. Now we saw that in general, let me change color. We saw that in general, our transformation was linear. Okay, and that means that we can write for arbitrary differentials dx bar squared minus c squared dt bar squared. We know that the transformation is linear. So the dx can be written in terms of dx, dy, and dz, and dt with no bars. And similarly, dt bar could be written in terms of dx, dy, and dz, and dt, okay, with no bars. So a linear transformation from unbarred to barred coordinates can be written as some constant a, dx squared, plus some constant g, there will be cross terms, dx and dt. And finally, we'll have some other constant d, dt squared. Okay, and this is due to the linearity that we just saw. Okay, so this is true for arbitrary differentials. So our goal is to find what these constants are. Okay, and yeah, I'm not sure I said, but we're here restricting to just the x and t coordinates, okay? So we're restricting to motion along one spatial dimension. We can generalize to include y and z, but just overly complicates things. Okay, so in general, this is dx0 squared plus dy0 squared plus dz0 squared, but we get the full picture if we just consider x and t. So let's find these constants somehow. And to do so, we go back to our little thought experiment with the light ray. And let's label these equations. Let's call this 1, let's call this 2, and let's call this 3. Okay. And from 1, we know that c squared dt0 squared is dx0 squared. Okay. So if this is true for an arbitrary differential, it must be true for the light ray case that we're considering. So we have that dx0 bar squared, this is our light ray coordinates, minus c squared dt0 bar squared equals a dx0 squared plus g dx0 dt0 plus d dt0 squared. Okay, and this must equal 0. Okay, so let me call this equation, this is 1 again, basically, just rewritten. And let's call this equation 4. Okay, if we put equation 1 into 4, this implies that dx bar 0 squared minus c squared dt 0 squared equals a, and instead of dx0 squared, we're going to write c squared dt0 squared. So plus g dx0 is plus or minus c dt0. Okay, we've got a dt0 here, so this is dt0 squared plus d dt0 squared equals 0. Let's call this equation 5. Okay, so equation 5 is telling us that, so it all involves dt0 squared with some constants. So it tells us that a, c squared, plus d, plus or minus gc equals 0. Okay, and if you think about this, a solution will be g equals 0 and a equals minus d over c squared. Okay, so by considering what happens with the light ray, we've found our constants. So we find that for arbitrary differentials, dx bar squared minus c squared dt bar squared equals, so g is 0, we have an a dx squared, and here's a, and let's call this k. So this is k dx squared plus g, the cross term 0, and we have d, which is minus c squared k dt squared. Okay, so this equals k dx squared minus c squared dt squared. Okay, so we've got a very important result. Dx bar squared minus c squared dt bar squared equals some constant k times this thing but unbarred, dx squared minus c squared dt squared. So the some constant k, and we've thought about frame s bar moving away from s with velocity u, but there's a symmetry to this system. So if you're in s, you see s bar moving away with velocity u, but if you're in s bar, you see s moving away with velocity u. So we could equally have redone things and ended up with a k on the left hand side. K dx bar squared minus c squared dt bar squared equals dx squared minus c squared dt squared. Okay, and this can only be true. These star and star star, these can only be true together if k equals plus or minus 1. But if we think about our two frames, S bar is moving away from S with velocity u, and if this velocity u goes to 0, then we expect the two frames to describe the same thing. Okay, so as u goes to 0, we want dx bar, all the coordinates, equal to dx, all the coordinates. So we have to choose the k equals plus 1 result. Okay, so we find a very important result, that this thing in the round brackets equals this thing, which is the same thing without the bars. And I will clean the board and we'll write this out more explicitly, this result, and see what the consequences are. So as a brief recap, we've made a perfectly reasonable assumption that our space and time must be homogeneous. And we've used the fact that if the laws of physics are the same in all inertial reference frames, this is the second postulate of special relativity, that the coordinate transformation between the coordinate differentials must be a linear one. Okay, and then we wrote down the linear transformation with some constants, and we tried to find the value of those constants. And we used a thought experiment of a light ray. So turning on a torch being one event, and the second event being when the light from the torch hit my hand. And that thought experiment allowed us to fix the constants in this linear transformation. And in doing so, we found a very important result. We found that for two events separated by dx in space squared minus c squared dt squared, and let's put bars on these. So these are two events separated by dx in space and dt in time as measured in s bar. We find that this thing equals dx squared minus c squared dt squared, where this thing represents the coordinate change between two events measured in s. Okay, so these are equal. So the change in x minus c squared dt bar squared in s bar equals the change in dx squared minus c squared dt squared as measured in s. And actually we only considered one spatial coordinate, x. We didn't think about y and z. And if we had have done, then we would have seen that this becomes a more general result, that dx bar squared plus dy bar squared plus dz bar squared minus c squared dt bar squared equals dx squared plus dy squared plus dz squared minus c squared dt squared. Okay, and these are for arbitrary differentials. Okay, so this tells us that we have a quantity, let's call it ds squared, equals dx squared plus dy squared plus dz squared minus c squared dt squared. And this is an invariant, i.e. it's the same in all reference frames. Okay, and this is an important quantity, and it's called the interval, invariant interval. So we found a quantity that has units of length, length squared. Okay, so speed times time gives us the length. So we've got, and it's invariant between two inertial reference frames. So this tells us that we're working with a metric space, and this defines our metric. So we can write this ds squared as a dx, let me use mu as the index, and then we've got a metric, and in special relativity we don't call it g, we call it eta, and it's got two Greek indices mu and nu for the rows and columns, and then we have a dx nu. Okay, and these are repeated indices, mu, one upstairs, one downstairs, and one downstairs nu and one upstairs nu, so we've got a double sum here over mu and nu. Okay, and if we call dx mu the four coordinates c dt, so c is the speed of light times time, that gives us the length, then dx, dy, and dz, and mu runs from 0, 1, 2, 3. Okay, so the 0th index is our time. Then to get this result, we need a minus on the time and a plus on all the space indices. Okay, so this must be c dt, dx, dy, dz, and then we've got a matrix, and this matrix must have a -1, a +1, a +1, and a +1. It's a 4x4 matrix that's diagonal and has zeros everywhere else. Okay, and then we've got the dx nu, c dt, dx, dy, dz. Okay, so this thing is our Minkowski metric. Which we call eta. Okay. And we wrote down ds squared in terms of the unbarred coordinate, but we could have easily, or just as well, have written it down in the barred coordinate. We could have written down that ds squared was dx bar mu, eta bar mu nu, dx bar nu. And if you think about that, then you'll see that eta bar mu nu must equal eta mu nu. Okay, and they're both equal to this thing. Okay, so our Minkowski metric eta is a diagonal matrix, diag, with signature -1, +1, +1, +1. Okay, and you'll see that different books maybe have a +1 here and minuses for the other three, the three spatial coordinates. And that's because if you look at this equation, then we could put a -1 in front of each side and the equation will still hold. But to be consistent, then you need to flip the signs here also. Okay, so there's two different conventions. This is the convention we use, and we'll stick to through the general relativity part 2. Okay, so we've got that in some 4-dimensional coordinate system, and this is our Minkowski space-time. Okay, where time and space are on an equivalent footing. Then we have a metric that's -1, +1, +1, +1. And this metric is the same in all inertial reference frames. So we saw that if we have a constant metric in one frame and we make a coordinate transformation, if that metric is also constant in the other inertial reference frame, then the transformation between the coordinates must be linear. Okay, so we have a constant metric. In both coordinate frames, S and S bar. So this means that we have a linear transformation of the coordinates. So xi to xi bar. Okay. So the barred coordinates must be able to be written in terms of the unbarred in a linear relationship with only single powers of these unbarred coordinates. And it's this linear transformation between coordinates from one frame S to S bar that we'll now focus on and we'll study the implications of.